Thank you so much for watching the latest AI Weekly update from Henry AI Labs. We have some really exciting new deep learning papers and ideas, as well as some new datasets and some new coding frameworks like a JAX 101 tutorial and the latest on the AutoNLP tool from Hugging Face. The first paper we'll cover this week is Behavior from the Void, Unsupervised Active Pre-Training. We've seen a lot of advances in contrastive learning and computer vision. These describe ideas like SimCLR, MoCo, contrastive predictive coding, the Suave clustering algorithm, bootstrap your own latent, SimSciM, and then the next paper we'll explore, Barlow Twins. So contrastive learning has been really successful at learning representations from unlabeled data. And this has been used in the reinforcement learning framework before in a paper titled Curl. In Curl, what you do is you take in the high-dimensional pixel inputs and you map it to two separate update functions. So it's a multitask learning framework where on one end you have the MoCo-style contrastive task, and then you have the Q-learning updates. The gradients flow back through the representation from both loss functions. So the idea behind Behavior from the Void, Unsupervised Active Pre-Training is to use contrastive learning in order to facilitate the exploration problem in reinforced learning, as well as kind of doing this unsupervised representation learning in the pre-training. So the idea is you're collecting all this data through exploration and you're trying to do diversity search, novelty search. You're trying to search for a new state that you've never been in before. And the way that that's measured is by using this contrastive learning to determine if the state is new or not with this non-parametric entropy estimator thing. And then you also are learning the representation as you collect all this data and build up that contrastive lookup table to determine if it's a new state or not. So on the topic of contrastive learning frameworks, we have a new one, which is Barlow Twins, self-supervised learning via redundancy reduction. And it does feel like the contrastive learning frameworks are advancing almost as quickly as new designs to the transformers. So the common problem of one of these frameworks called bootstrap your own latent is that it doesn't make sense why it doesn't output constant representations for every input image. The bootstrap your own latent framework has the same kind of style of taking an image, putting it through two clones of the neural network, Siamese networks, and then trying to maximize the similarity of these representations. So the idea behind Barlow Twins is that instead of just maximizing dot product similarity or cosine similarity, we're going to be doing this cross correlation matrix and trying to make it equal to the identity matrix so that we have this decorrelated vector along the diagonal. So it's an interesting new loss function. They provide more details about it and they compare it with some other algorithms in the paper. This is where they provide the loss function and they'll compare it with other algorithms. And it's another interesting idea in self-supervised learning. And surprisingly, again, this framework, which is really so similar to the paper SimSciM, this paper, which has a pretty simple looking framework, is able to perform just as well as these other ideas like SimCLR, which requires really large batch sizes. But one thing about this is it is going to require high dimensional output vectors, and we'll discuss that more later in the video. Next up is one of the more out there ideas in deep learning. Pre-trained transformers as universal computation engines. I already thought that the idea of transfer learning was kind of interesting and counterintuitive, that you can train a model on one dataset and then have it transfer that representation onto a new dataset. Well, this paper is going even deeper than that and saying that not only can you train it on one dataset in the same domain, like say Wikipedia, fine-tuned on IMDb movie reviews, this is saying that it can be modality agnostic. So you could train the transformer on Wikipedia and then fine-tune it on CFAR10 image classification or this tape protein property prediction benchmark. So it's a really interesting idea of trying to fine-tune these transformers onto data sets of other domains, as well as an interesting detail is that they're not going to fine-tune the entire transformer. They're only going to fine-tune 0.1% of the parameters and all these other interesting details that we'll get into later in the video. From Google's AI blog is an interesting new approach to thinking about generalization. So the idea is that instead of thinking about generalization as comparing the error on your training set as well as your testing set, we're going to compare it between the real world setting and the ideal world setting, or more particularly where we repeat data batches compared to where we have an infinite data stream. So one thing that really drew me to this paper is the way that they create this ideal world test, and the way they create this infinite data stream is by training a flow-based model, this diffusion, denoising diffusion probabilistic model, some title like that. I don't know too much about flow models. It's a generative model compared to, say, VAEs, GANs, autoregressive models. There's something different to the normalizing flow model that I'll describe more later in the video, but they train this generative model to produce 6 million CFAR10 images. So CFAR10, it usually has 50,000 images, and you usually repeat the batches like this. So they're going to come to this conclusion about training curves based on comparing these two different settings where you either repeat batches of data or you have a never-ending stream of data. I really love the creativity in this next paper titled Knowledge Evolution in Neural Networks. So the idea here is a play on evolutionary search as well as the lottery ticket hypothesis. So what you're going to do is you're going to form a fit hypothesis and a reset hypothesis, and the fit hypothesis will be a potential candidate for the lottery ticket hypothesis. So if you know the paper, The Lottery Ticket Hypothesis, the way they find the sparse subnetworks is through the use of iterative magnitude pruning. This is where you iteratively mask out the weights that are 0, train it for a little bit longer, then go back, mask out the small weights, and so on. It's this iterative algorithm of finding these subnetworks compared to this evolutionary search idea, where you'll propose a potential lottery ticket and then you'll perturb the rest of the weights to try to help the lottery ticket itself learn the subnetwork. But overall, I think just the creativity of this framework of combining an evolutionary search with an idea like lottery ticket hypothesis is really interesting. It reminds me of a paper that we covered last week that I'll get into more when we actually are going deep into this paper. Compression with implicit neural representations, abbreviated as COIN, is a purely genius way of thinking about how to compress data with deep neural networks. So the idea is that you learn the RGB mapping for each XY position in an image, and then you store the weights that had learned that mapping. So you overfit to the image by learning this perfect mapping, and then you store the weights as the compressed representation. So in my opinion, this is a truly novel way of thinking about data augmentation with deep neural networks, and I'm excited to get into a little more of the details about how this works. Next up is another really interesting idea with respect to applying deep learning for healthcare and for disease detection with medical images. So we've seen so many papers that do things like skin cancer classification or chest x-rays. Chest x-rays, especially with COVID, have become a more popular application, and we've seen more of these data sets be released. So the idea behind this paper is how well do these models generalize to diseases that they haven't seen in the training set. So in our training set, we have these different labeled diseases from these chest x-rays, and then there could be unseen diseases. So it's kind of like the few-shot learning problem, where we're trying to see what happens when we have these unseen diseases. So it's a little bit of an adaptation problem, but it's also kind of an out-of-distribution problem, where we want it to be able to at least have a sense that this is a new disease, rather than just classifying it into what it has seen or classifying it into no disease. So it's a very interesting setting for very interesting application, important application for thinking about this problem of out-of-distribution detection with new class labels. We've seen so many advances in natural language processing with things like information retrieval, question answering, summarization. There are so many new advances that we can expect that there are going to be some really exciting new search engines built soon, and Haystack is a great example of an open source search engine that's combining all these latest advancements. And this blog post from Brendan Chen, Haystack, the State of Search in 2021, is a really awesome read describing many of these different ideas in Haystack, the retriever-reader pipeline, how you do information retrieval, how you collect that information, and how you then return some kind of answer or perform some kind of task. This idea of using the retrieval augmented generation model, which is where you have a language model that is seeded with some kind of context as its input as well. The idea of using these text summarization models with the Pegasus pre-training task, and all these different ideas of the Haystack open source semantic search engine. And this is a really exciting blog post. I really enjoyed reading this. So following the hype and excitement of Haystack, the State of Search in 2021, we will bring this down to earth a bit with this paper, Hurdles to Progress in Long-Form Question Answering. So long-form question answering is this idea of having natural language processing models that write a paragraph-length answer. This could be a chatbot, this could be a question answering system, or this could be a summarization system, such as taking in this entire research paper and then generating a summary of it. And a really famous data set of this is the Explain Like I'm 5 data set, and this paper is going to report all the different problems with their system, even when their system topped the public leaderboard. So some of these data sets, they maintain these websites where they have a public leaderboard of who has the best score with respect to the metrics, in this case this Rouge L score, and these authors are reporting all of the different problems with their system, even though it tops the leaderboards. And they show this really well with this figure that we'll get into as we go deeper in the video. Next up, we'll look at some of the really exciting datasets that have come out this week as well, starting with CUAD, an expert annotated NLP dataset for legal contract review. So what this is you have these different legal contracts, and they've been annotated with different outputs based on question answering, or maybe it's entity recognition, or all these different kind of things that are contained in these legal contracts. So one of the quick things to take away before going deeper into the video is how expensive this dataset is to construct. So they note the cost of this is over $2 million to build the CUAD dataset, because of the time it requires to densely annotate this data. So I think that makes it just right there, makes it a pretty exciting interesting new thing in deep learning datasets. We also have a new revision to the wilds dataset, a benchmark of in the wild distribution shift. So they've added a new code completion dataset as well as some other updates that we'll get into later in the video. And this is a really exciting dataset that shows real world test set distribution shifts, which is one of the most talked about problems, this issue of generalization and the issue of measuring it based on the train error to the test error when they're drawn from the same data distribution. And this is an actual collection of how that test distribution will shift in the real world. So also from the Google AI blog is a new environment known as Paired, a multi-agent approach for adversarial environment generation. So if you've seen things like Poet or the enhanced Poet, where you have this co-evolutionary search where you're learning a bipedal walking agent as well as the environment that it walks on, this is the idea of having an adversarial reinforcement learning agent design the environment for the other agent to learn in. And the problem with this is that these agents are usually too good at designing a hard environment. So shown on the far right is an example of the adversary quickly learning how to construct this maze that is completely impossible for there's no path to the green square. So this is a way of regularizing this and then providing this environment for other people to use and test out this framework of having an adversarial controller construct the environment and then also having an agent that learns in that constructed environment. CheXseen is one of the most cutting-edge frameworks for implementing deep learning and particularly automatic differentiation, where we want to differentiate through these mathematical operations in the forward backward passive neural networks without having to actually write any of that gradient code ourselves. So this tutorial is presenting some of the latest ideas in JAX. You have a JAX quick start, how to think at JAX, JAX is sharp bits, some of the common mistakes that people make. And now we have this new tutorial, JAX is accelerated NumPy, comparing the differences between JAX and NumPy, explaining this XLA compiler thing, automatic vectorization, advanced automatic differentiation. I thought this personally is what I think is the most interesting. This is how you do things like say mammal or shampoo, or say the straight through estimator where you have discrete operations in your computation graph. And then also pseudo-random numbers, parallel evaluation, and stateful computation. So in this video later, we'll have a quick look at each of these tutorials. They'll have collab notebooks, which is a really great new way of communicating these deep learning coding tutorials, because you have this cloud runtime with the GPU. It's really easy to access. And we'll have a look at this JAX 101 tutorial. So coming from the JAX 101 preview, which is kind of as close to the ground as possible, where you're really controlling all these different details that go into constructing a deep neural network, now we're looking at the other extreme, which is Hugging Face's AutoNLP tool. So similarly to maybe like these previous approaches, things that were popular like say MATLAB, where you're just clicking buttons to train neural networks, now you have this really simple interface to use cutting edge natural language processing. So Hugging Face already implements tokenizers, come right off the shelf. The data sets are built into Hugging Face. They have like BERT for sequence classification, where that whole entire pipeline of constructing the model, making the proper input-output dimension is already taken care of. And they even implement the evaluation metrics. So now they're clustering all that functionality into one tool, the AutoNLP tool. So the AutoNLP tool are these end-to-end pipelines that do all of the pre-processing, all of the model fitting, and now even the hyperparameter search is going to be contained in these command line interfaces for training natural language processing models. And it's really an exciting thing, this AutoNLP from Hugging Face, that will make more and more people excited to use natural language processing. We began this video by presenting some of the most cutting edge ideas in contrastive learning, Behavior from the Void, which is using it for exploration and reinforcement learning, and Barlow Twins, which is the latest modification to the framework, particularly an extension on the Bootstrap Your Own Latent framework. And we'll end the video by looking at the latest in a coding framework for having reproducibility with these large-scale contrastive learning experiments in VISSL. So VISSL came out as a part of, last week we covered Facebook's SEER representation learning, where they were testing the SWAV clustering algorithm out with a RegNet architecture on 1 billion or 2 billion Instagram images. So VISSL is a framework for trying to organize these large-scale self-supervised contrastive learning algorithms. So we have these YAML files in VISSL that organize which framework you want to use, say SimCLR, MoCo, SWAV, and now we have these other things like implementing the zero optimizer for trying to do this optimization with this large scale training, because contrastive learning is large scale experimentation. So we have this new framework of trying to organize this, and we'll look at the YAML files for constructing these experiments, and we'll look at a couple of the collab notebooks that they provide. And I'm also really interested in this idea, if we quickly preview before getting into it, how they implement large-scale training as a part of this library. And we also have the benchmarks, the feature extraction, trying to standardize these self-supervised contrastive learning frameworks so that we can make sure that these experiments are rigorous and are really making progress. And I personally, something that I think is interesting is how, say, the Barlow Twins, which is this cross-correlation matrix thing, is able to perform just as well as all the previous approaches. Not that the cross-correlation matrix thing is uninteresting, but to think that small extension on the two representations from the same network is as good as, say, the momentum encoder queue with these large negative batches is that something that I think is really surprising. So we'll end the video by getting into this VISSL coding tutorial, and overall we have a lot of different exciting things to cover in this AI Weekly Update. The headline of this new AI Weekly Update is Behavior from the Void Unsupervised Active Pre-Training. So as shown in these plots, the green plots are the results of active pre-training compared to the data regularized Q-learning in the paper titled Image Augmentation is All You Need, as well as using an ImageNet pre-trained representation. So we see this up and to the left because this is really what we're interested in real-world robotics is data efficiency. We want these vision-based robotic systems to be able to learn quickly, not just reach really great performance with a massive amount of data. But in either case, we see the green performance is performing better on these DeepMind control suite tasks. So the core idea is to use contrastive learning for exploration and for searching the environment and finding data. And so let's jump right into the key idea, which is this idea of this particle-based entropy reward. So the model, the agent, it explores the environment and it gets a new state. So this state is converted into a representation vector through the encoder, and then we have a projection normalization into this contrastive loss where we're updating and learning the representation with all of the states that we've seen. But now we're going to get our exploration reward from this particle-based entropy reward. So we fetch the k nearest neighbors from this new state representation, this green representation, and we're going to compute how similar it is to these k nearest neighbors of the other states that we've encoded in this representation. So this is how it's going to be trying to find a new state based on its dissimilarity to the nearest neighbors in the representation space. And that's how it's going to be pursuing exploration and trying to find these novel states and pursue exploring the environment. So with a quick understanding of this particle-based entropy reward to use contrastive representations to signify that this state is actually a novel state in the task of exploration, let's look at the overall algorithm to put all this together. So the algorithm 1, training active pre-training, randomly initialize the encoder F, randomly initialize the policy and Q learning networks. So for I1 to T is this hyperparameter of how many steps you want to do this for. Receive the state from the environment, take an action, the policy mapping to an action from the state, and then you get the next state S prime. And it's also important to know that this is active pre-training that does not use the reward. So the reward of the environment itself is completely left out of this pre-training process. It's only about representation learning with the state action, next state, pairs. And the way that this is done with, say, the soft actor critic value thing where you have the policy and then you also have the value function. The value function sends a signal to the policy to do this TD temporal difference error update is by using the Q prime from the critic derived from this particle-based entropy reward. So let's go back to putting it all together. So you sample a batch of data by just exploring the environment, and then you train the neural encoder F on the mini batch with equation 14. Equation 14 is the SimCLR loss. So SimCLR loss is trained to learn representations with this data set D. So now with that representation from F, you're going to compute the R sub APT, the active pre-training loss, with this loss function where you have the distance between the uniqueness of these states that have been explored. And then you're going to use the uniqueness of the states that have been explored to update the ground truth temporal difference error for the learning of the actor in this loss update with Y sub I. So Y sub I becomes the active pre-training update plus this previously estimated Q value of the S prime, A prime mapping where you have the next state. And this is just like the technicalities of how you do this temporal difference update in the actor critic learning framework. But what matters for the sake of understanding this new paper is understanding this idea of discounting the reward, learning a contrastive encoder, and then using that new reward from this thing to do the temporal difference update. So overall, this is the active pre-training algorithm, and the authors end with some questions that summarize the key findings and outstanding questions from their study. But before going into this, I want to backtrack a little bit to cover this idea of how contrastive learning and data augmentation have been improving vision-based reinforcement learning, and obviously the really exciting application of that is vision-based robotics, where we've seen things like OpenAI solving a Rubik's Cube with a robotic hand that uses pixel inputs. We've seen folding towels, closing drawers, tossing things. all these really impressive robotic applications that operate in this reinforced learning framework with visual pixel-based inputs. So I want to explain quickly how, say, curl or the data regularized Q-learning thing is different from active pre-training. So in active pre-training, again, we're throwing away the reward and we're using this as an exploration strategy. So we explore our environment and then learn a state representation function. And that's the key idea, is representation learning. This is the idea behind curl. You take in the high dimensional pixel input as, say, you're a robotic agent that is looking at the world visually, and you're going to form a query and a key encoding by taking two data augmentations of the original input image frame, and then one is going to be passed into the Q encoder and another is going to go into the momentum encoder, which is the momentum contrastive learning framework. And now you're going to have a contrastive loss on the representations from Q and K, the query and the key, from this data augmentation transformation of the same input, and this is used for representation learning. So this loss function from the negatives gets propagated into this encoder's parameters, and then it gets integrated into the representation as it does Q learning updates or actor critic, whatever framework you're doing with this representation of the original pixel input. This is also well shown in this image more visually. You have the replay buffer, you have these observations, you form data augmentation pairings of them. One goes through the key encoder that is learned with the momentum running average of these parameters. It's a Siamese network. And then you have the contrastive loss with these two, as well as this getting passed into the reinforced learning updates. So the other interesting way of using data augmentation in vision-based robotics that has also been advancing the state of this field extremely quickly is the data regularized Q-learning, and image augmentation is all you need. And this is a pretty simple idea to understand. What you do, described in these three different summarizations, is you transform the input image by averaging the Q target over K image transformation. So what you do in actor critic is, let me get this, is you have the temporal difference error. So you have this VST plus 1. This is bootstrapped from your critic. So the critic is going to be estimating this, what kind of trouble have you put us in by taking us to this new state as you do this value of the state. This part you're going to get you get a reward immediately from the environment. The environment returns state next state reward pairs. So you always immediately get the next reward, and then you need to use your critic to bootstrap how much trouble are we in now, or is this a good position to be in? So you're going to average the Q target over data augmentations. You use data augmentations to form a kind of ensemble learning, and then you're also going to average the Q function itself that does the state action mappings with the transformations as well, using these equations. So hopefully that was a decent enough overview of these two papers, curl and then the data regularized Q learning, and image augmentation is all you need to have a sense that contrastive self-supervised representation learning and data augmentation are both massive drivers of progress in vision-based reinforced learning, like what's being used in robotics. And some robotics also use sensors, but this idea of vision-based robotics is definitely accelerating quickly with some of these really exciting papers. So finally, let's end with some of these questions that they pose. How does ABT compare to supervised baselines? Comparing it with in these plots, they're comparing it with data regularized Q learning. How does ABT compare to supervised reinforced learning? So just directly going after that reward compared to having this pre-training phase. So instead of throwing away this reward, obviously it wouldn't be the same framework at all, but instead of throwing away this reward, you use the reward to learn the Q functions in deep Q learning, where you're mapping a state action to a predicted reward, and that's the idea of Q learning. So then question 3, how does ABT compare to unsupervised pre-training? This is another strategy for doing unsupervised pre-training by mutual information maximization, differently from this idea of this this particle entropy thing. So it's a different strategy for doing this, a similar framework. How does ABT compare to unsupervised reinforced learning? So this is another algorithm for throwing away the reward and then trying to learn representations and then fine tune it with the reward quickly. How does APT behave differently from unsupervised RL on Atari? So also evaluating question 4 on the Atari benchmark as well as DeepMind control suite, and then ablation of each component of APT in table 4. So overall, it's a really exciting new algorithm for doing this idea of novelty search, diversity search, and then practically implementing that in high dimensional environments with the contrastive loss and these contrastive representation learning frameworks, and particularly this new particle-based entropy reward idea of taking the k nearest neighbors and using that to assign a measure of novelty to the explored state. New in deep learning this week, we have a new framework for contrastive learning, Barlow Twins, self-supervised learning via redundancy reduction. So the name comes from H. Barlow's redundancy reduction principle, as stated later in the paper, this idea that the goal of sensory processing is to recode highly redundant sensory inputs into a factorial code, a code with statistically independent components. And this is similar to the idea of the information bottleneck. Described here, a distortion function that measures how well y is predicted from a compressed representation t compared to its direct prediction from x. And this is also shown really well at the end of the paper Appendix A, comparing this idea of how well do you predict Z from this compressed representation. So Z are the compressed representations, Y is the data augmentation views of the original image, and this idea of these flows of information is the information bottleneck principle. So more concretely, what is the idea of Barlow Twins? Barlow Twins is the idea of having this new loss function where we have the cross-correlation matrix, and we're trying to make that equal to the identity matrix so that we have decorrelated dimensions of the representation vectors. So this is very similar to bootstrap your own latent. We take an original image, except for this time we're not using a momentum encoder to have a running average of the parameters of this other network. We're just passing in the same network, like a Siamese network, and we have these two representations. We form the cross-correlation matrix through this calculation, and then we try to set that to be equal to the identity matrix. So some complete pseudocode is shown here if you're curious about how to implement this idea and how to calculate these cross-correlation matrix, how to take the loss between the identity matrix, and so on, how to do this loss. So this is the idea of the Barlow Twins. Some of the key differences really is just this use of the cross-correlation loss and then getting away from ideas like the stop gradient operation in SimSciam, the moving average of the weight updates in Bootstrap Your Own Latent, and also there's no projection head like SimCLR. I think almost all of these papers have it go from Z and then also into some other space to apply the loss function. So it doesn't do that either. And so it's a really simple framework, probably the simplest framework that's come out, maybe tied with SimSciam. And so interesting new approach to contrastive learning. So with the basic idea of the Barlow Twins framework, let's get into some of the results. So the first result that they present is the accuracy of how well this performs when you take the representation and then you put a linear model on top of it to classify ImageNet images. So it's really surprising to me that the Barlow Twins is able to perform similarly to the SWAV clustering algorithm. So the SWAV clustering algorithm, it has this I made a whole video explaining this if you really want to do a deep dive and are really curious about what SWAV is, but it's this online clustering algorithm that has this clever technique of speeding up the online clustering using this Sinkhorn NOP algorithm, and basically it has a lot more structure than just applying this new loss function between representations of a copy of a network. And it has this projection thing, but anyway, so I always find it surprising when these new techniques, so SimSciam is another simple framework, that perform as well or better than, say, MoCo. MoCo has this momentum encoded Q, and then this prototypical representation learning thing is kind of like an earlier edition of SWAV from Salesforce research. So I think it's just amazing that this new technique that is a lot simpler to implement performs just as well as these other strategies, even though some of them like SimSciam and Bootstrap Your Own Latent are pretty simple as well. So then we look at the semi-supervised learning results. This is where you have you have some labeled data as well as some unlabeled data. And it looks like in this case, there's probably some kind of additional, they're not using the full data set, so you only use 1% or 10% of the labels, and that's why it doesn't perform as well as using all the labels. But this is a really interesting setting because this is the idea of having a self-supervised representation that can be fine-tuned to any task and then overcome the challenge of learning from limited labeled data. So then we also see the results of transfer learning where we take a similar idea is the high level idea of this is we want to have one representation that's been learned from self-supervised learning, and then we can fine tune that to say learning from limited labeled data, or maybe in extreme cases like few shot or zero shot generalization. And we want to be able to learn from limited labeled data on a new task. And we also want to be able to transfer out of domain to these other kind of data domains. And then we also try this for other computer vision tasks like object detection and instance segmentation. So then we get into some of the ablations of the details of the algorithm, and then the most interesting thing I think is this projector dimensionality thing. So at the end of the representation learning framework, you have some compressed vector representation, this Z sub A thing. So this is the product, this is the representation of the data. And what's interesting about this, and it makes sense intuitively because you're trying to decorrelate the dimensions of the vector. So obviously it makes sense that you would need a larger vector to represent the data. But you see this performance improvement with respect to increasing the dimensionality of this Z vector. So going as far as 16,384 in that last dimension of the vector continues to improve the performance. So I think that's really interesting. And you'd also think that that would make the similarity alignment in a much easier task. So it's also interesting that that doesn't cause a different kind of representation collapse with contrastive learning, because if you have this massive vector and you're trying to make them similar, you can just isolate this really specific point in this high dimensional space. But I guess the cross-correlation matrix thing is kind of avoiding that solution. So with that structure and this increasing functional improvement of the projector dimensionality, this is probably a really interesting trend for future work as they do state in their paper. This next paper explores a very ambitious idea, pre-trained transformers as universal computation engines. So when I was originally introduced to this idea of having one representation for all of image data, so say this idea of pre-training on ImageNet and then you have this one feature extractor for transfer learning that's useful for all these different downstream applications. It could be, say, dog breed classification that's originally sourced from representation from ImageNet, or say landscapes, or this kind of idea of having one representation. I thought that was a pretty ambitious idea. And now it looks like we're even graduating in this ambition with the idea of having a single model that can be trained on any modality, so any data domain, language, images, or whatever, and then fine-tuned into a different modality. So they test, particularly at the end, they test this homology thing where they're testing a protein fold prediction problem from this transformer trained on language modeling or something like that. So trained on text data and then fine-tuned on this protein folding prediction problem. So the first question is, how could this possibly work? And the idea is that you take any kind of data domain and then it's eventually transformed into this matrix of dense distributed representation. So discrete text tokens get mapped into this embedding table where you now have this matrix of dense values like 0.7, 1.3, and so on, similar to an image pixel grid once you've normalized it. So you have a similar kind of representation of all data once they hit these matrices full of dense distributed representations. So the idea is that you can identify feature representations that are useful for arbitrary data sequences that enable this downstream transfer to different modalities. So it reminds me of these papers, like recently I did a video summarizing modals, modality agnostic automated data augmentation in the latent space. This is looking at this idea of augmenting data directly in these intermediate feature spaces by looking at different strategies of how to interpolate, extrapolate within these intermediate feature vectors. And other papers do this as another example of doing adversarial augmentation in embedding spaces, and the ultra data efficient GAN training strategy, another technique of looking at how to augment data in the latent space in these intermediate feature embeddings. And then also this idea, and then the next idea to cover actually, is this idea of not fine-tuning the whole network. So pivoting a bit from this idea of universal representations, now let's talk about how they actually do this. So they use the frozen pre-trained transformer. So they're not going to be fine-tuning this entire, say you have a 10 billion parameter language model, that would be overkill for something like CFAR10, say. So they're going to be fine-tuning a small percentage of it, and also it saves the computational cost dramatically with respect to doing these experiments and so on, and it makes this whole thing more practical and reasonable to only fine-tune a small percent of the parameters. So they only fine-tune 0.1% of the actual original model. And that reminded me of this paper, Training Batch Norm and Only Batch Norm on the expressivity of random features in CNNs. And this is showing that just those gain and bias parameters in batch normalization, these two parameters, are able to heavily influence the output. So we see how you don't need to fine-tune the entire network always to do this kind of transfer learning with fine-tuning. So this is a pretty long and really well-written paper, so let's have a quick sense of the different evaluations that motivate the study to get a sense of the paper instead of doing a complete dive of each section. So the first question is, can pre-trained language models transfer to different modalities? That's a high-level overview of the paper, and now we're looking at some more individual components. What is the importance of the pre-training modality? Say, can we pre-train on text and then fine-tune on images, or should we pre-train on images? So overall, this is such an interesting idea because we've collected so many different natural language processing data sets. Say, look at the Hugging Face dataset search to see some examples of this. We also have so many image data sets as well, like CFAR10, CFAR100, ImageNet, STL, Street Views house numbers, there's all these different data sets, and you can see maybe the Torch Vision library or the Keras datasets are good examples of just seeing all these different datasets that have been collected for these, I think particularly text and language, maybe also some audio datasets, but those are the most common datasets. So what's the importance of the pre-training modality as you then take this universal representation to a different data domain? Then how important is the transformer architecture compared to the LSTM architecture? How much is the transformer really this new architecture that seems to be changing everything in deep learning? How important is this particularly for the success? The next question is, does language pre-training improve compute efficiency over random initialization? So this is the idea, if you pre-train on language data and then fine-tune on this protein folding data, is that going to improve compute efficiency? Will it learn quicker compared to random initialization with the same network architecture? So this is the idea of really testing if the representation that you're transferring is useful, if not just the architecture itself and disentangling that factor. So the next question is, do the frozen attention layers attend to modality-specific tokens? So this might be hard to define in, say, images, but you could maybe do something like grad cam or these different kind of visualization things that they use to try to see, interpretability in that kind of area of research. Does freezing the transformer prevent overfitting or underfitting? So an interesting dimension of this is, say you're transferring this 10 billion parameter. This is a problem in all of natural language processing, is you're trying to fine-tune these giant models onto limited labeled data sets. So the pre-train then fine-tune, and you pre-train a massive model, fine-tune it on a small, pre-train a massive model on a massive data set, fine-tune it on a small data set. And so this idea of freezing the weights only training 0.1% of the weights, is that going to help prevent overfitting, or is that going to underfit because you're not fitting enough of the model? Then does performance scale with model size, scaling up, say 5 billion, 10 billion, so on? Can performance be attributed simply to better statistics for initialization? So it's kind of disentangling, is this representation transfer thing really such a esoteric, poorly understood idea, or is it really just statistics of these initialization parameters? Does fine-tuning the self-attention and feed-forward layers further improve performance? So looking at exactly what we're fine-tuning with respect to the model, similar to these questions like 3.6. Then which parameters of the model are important to fine-tune? Again, 3.9, 3.6, further looking into this idea of what of the transformer we're going to be fine-tuning. How well do the trends hold across other transformer models? So I'm not sure if this is just referring to decoder only, encoder only, or encoder decoder kind of architectures, or if it's referring to things like linformer, performer, transformer, XL. So it's hard to say exactly what that might mean. Can we train a transformer by only fine-tuning the output layer? So that's another interesting idea. Freeze the entire feature extractor half, and then only fine-tune the classification head. So overall, this looks like a really interesting study on trying to see this cool idea, and you can see the quick results in figure 1 of fine-tuning this model on tasks outside of the original data domain. So training it on language and then fine-tuning it on image classification or protein folding prediction. So finally, before concluding on this topic of pre-trained transformers as universal compute engines, you might also be interested in this paper, Pre-training a Language Model Without Human Language. This describes this idea of, say, pre-training on amino acid sequences or JavaScript code, and then fine-tuning on the GLUE benchmark natural language text task. So this is another interesting paper if you're really inspired and interested in this area of research. Next up from the Google AI blog is a new lens on understanding generalization in deep learning, explaining the paper, The Deep Bootstrap Framework, Good Online Learners Are Good Offline Generalizers. So what they mean by this is online learners refer to the ideal world where you have an infinite data stream, and then offline learners refer to the real world setting where we have batches of data that we repeat through. So as shown in the paper, The Deep Bootstrap Framework, the key idea is instead of measuring generalization by studying the training error and the testing error and using this to define this concept of a generalization gap, we're going to compare the error when we're learning with an infinite data stream compared to repeating the same batches of data as is in the common framework for training these models. So the idea is that in order to simulate an ideal world test set, this is where I think this experiment gets really interesting. So what they do is they're going to train a generative model on CIFAR-10. More particularly, they're using a denoising diffusion probabilistic model. This is an example of one of these flow-based models, and personally I haven't quite gotten my head around this idea yet, but here's a good section on it that I read over the weekend in the survey paper, Deep Generative Modeling, describing normalizing flows and the high-level idea. And then here's another really great blog post if you're curious about this particular architecture of flow models, some idea of inverting these matrices for these transformations. And again, I don't quite understand it, but let's just call it a generative model. So they train a generative model on CIFAR-10, and they use it to generate 6 million images. So we've seen in generative models, say you take the GAN, for instance, where you can walk along this latent vector Z to produce a really smooth set of images, the transitions between them, and overall learn this data distribution that lets you produce 6 million images. And I'm not sure why it's then named CIFAR 5 million, but I assume that's just a typo between the two. But so they generate this massive set of CIFAR images such that they can simulate training where you don't repeat any samples. So with the general concept understood, now let's get into some of the results. So they plot these different plots with the multi-layer perceptron, the vision transformer architecture, and the ResNets, showing these small differences in the gap between the ideal world set and then the real world set. And I don't think there's anything to really take away from this plot. But here is finally what they end with. So the online optimization is how fast the ideal world test error decreases compared to how fast the real world training error decreases. And they say that you basically want to keep these two together. You want it to not learn too quickly in the offline setting and then still be able to learn in the online setting. And they use this to justify that when you're doing pre-training, you're helping it learn in the ideal world set. And then when you're using data augmentation, you're helping to slow it down in the real world set. So you're trying to have these two different learning curves develop together at once. And these are some of the effects of pre-training, showing that it does a better job of keeping these two curves aligned throughout training. So I think it's an interesting framework for thinking about generalization, and definitely an interesting idea of comparing this idea of an infinite data stream compared to looping through the same batch. The next paper for this AI Weekly update is Knowledge Evolution in Neural Networks. Last week we looked at the ultra data efficient GAN training, drawing a lottery ticket first, then training it toughly. So amongst other things like the use of data augmentation in this paper, they're showing that finding these lottery tickets is actually going to help improve with data efficiency. So finding the sparse subnetwork within the dense architecture is helping these networks learn with less labeled data. And in my opinion, that's kind of counterintuitive, but it seems to be working. And here's another paper that is exploring this idea of finding these lottery tickets for the sake of improving upon data efficiency. So we're convinced of the idea that the sparse subnetwork is going to be a more data efficient learner, but now we need a technique to find the sparse subnetwork from scratch. So the original lottery ticket hypothesis paper uses this thing called iterative magnitude pruning, where you prune away the weights to find the sparse subnetwork after you've already trained the dense network. We haven't yet achieved a really great way of finding these sparse subnetworks before we do any training. And there have been some proposals as cited in the paper, but this idea is to use an evolutionary search in order to find these sparse subnetworks. So we're going to propose a fit hypothesis, which is going to be a candidate sparse subnetwork, and then we have the reset hypothesis, which denotes the rest of the weights in the dense architecture, and we're going to be perturbing the weights in the rest of the network in order to try to find and improve the learning to convergence on the sparse subnetwork. Next up is COIN, compression with implicit neural representations, and I think this idea for compressing data with deep neural networks is absolutely genius. So one way of thinking about compressing data with deep neural networks that I've thought about is using an autoencoder. So you'd take an image and then you'd use an autoencoder to compress it to that latent vector Z that's a compressed representation, and then at inference time you use the decoder to decode these stored latent vectors, and all you have to store is the latent vectors and then the parameters of the decoder. But this idea is, instead of storing these latent vectors Z, you learn an overfitted mapping from each XY coordinate to the RGB pixel values for each of the images. And the images come with the compressed representation of the weights of the multi-layer perceptron. So all you have to store is these weights for each image, and that will be able to decode the image. So then one question you might have is, well, this kind of decoding might be expensive. It could take a long time to have to go inference in order to recover the original image. But as they describe later in the paper, is this an example of an operation that's embarrassingly parallel, where they use this. So embarrassingly parallel is the idea that you could really parallelize that inference across all the different coordinates and then have a single forward pass that re-renders the image. So they describe some of the different performances of compressing the data with this technique. And overall, I just think that this concept of encoding the data like this is really interesting. One of the most frequently discussed real-world applications of image classification is for medical image diagnosis. The idea here is that you would take an image like a chest x-ray and then classify it into one of these labeled categories by a doctor. So what this paper is testing is how well these datasets perform, or the models trained on these datasets perform, when they're seeing unseen datasets from the train set during inference time. So as shown in this figure that illustrates the training setup, they have a dataset that's labeled as no disease and then 3 different diseases. They're going to be evaluating how well they can detect these unseen diseases. And they're going to be doing this by using the final prediction layer, the final class logits, the penultimate layer, which I imagine is some intermediate vector representation, and then also the grad cam, where you project the gradients back onto the original input image in order to use these representations to fit an unseen disease classifier. So from these representations, fitting an unseen score. So it's a very interesting study of making these kinds of models practically useful. So the key insight of the study is about labeling and constructing these data sets. So as they say, they're able to detect any disease versus no disease in images with co-occurring unseen and seen diseases. So when they're trained on data sets that have a mix of both these seen and unseen diseases, they're more likely to be able to say that this is any disease compared to no disease when they're seeing this unseen disease. But if none of these images appear in the training set, they're more likely to classify these unseen images as no disease. One of the authors of this paper, CheXseen, has also published a really great Twitter thread describing these experiments. So here are some of the key questions. Can we detect diseases not seen during training? They designed this controlled experiment, and they find that models tend to falsely classify unseen diseases as no disease. So then question 2, is there a performance drop on labeled data sets? They find that the models are still able to detect seen diseases even when co-occurring with unseen diseases. So adding in the unseen diseases to the data set won't corrupt the performance on what has been labeled into the more fine-grained classes. And then can unseen diseases be detected without explicit training? So trying to take these representations and do some kind of added distribution detection just with these representations, and they show that that can be used. Next up in the AI Weekly Update is Haystack, the state of search in 2021. We've seen some really exciting advances in natural language processing, and Haystack is an open source implementation, going right to the what is Haystack documentation page if you're interested in this. It's an implementation of all these different ideas like retriever, reader, question answering, summarization, all these really cool techniques for developing the next generation of search engines. And quickly, I want to talk about this paper really quickly. I recently published a survey paper of reviewing these applications for COVID-19 with deep learning. And one of the ones that I thought was just the most interesting are these scientific literature mining systems. So taking all the latest advances in natural language processing and combining them into these search engines. So we have these document corpora, which are things like the CUAD-19 dataset, where you have all these papers with relevant information to COVID-19, and you're building these new indexes where you use, say, the Siamese BERT, as well as these TF-IDF BM25 vectors, and you use this to form these indexes to do retrieval. We've seen recent models like retrieval augmented generation, the Pegasus pre-training task for improving summarization, and all these really exciting advances. So I'm really excited about this idea of building these semantic search engines using these new data sets like scientific papers, or later on we'll look at the CUAD data set of contracts and things like that. So I really think that there's an exciting transformation in search that's being enabled by natural language processing. And here's an interesting open source effort, Haystack. This article describes some of the really interesting functionality in Haystack. So you have the retriever-reader pipeline where you can connect your own data set into Elasticsearch, SQL, Milvus, I've never seen this before, or the face thing from Facebook. So this is how you do the document encoding and then do the retriever half of, say, information retrieval, where you have to, you might have a data set of like 500,000 documents and you need to match semantic similarity with the query. So this can be a really challenging big data task, but it's facilitated with these GPU similarity searches in libraries like Face. So this is first describing this retriever-reader pipeline, and I really like this sentence. We are now able to ask fully grammatical questions in our searches and tackle complex and detailed queries which were beyond the scope of Control+F. So if you ever had a long document and you did Control+F to say search for some keyword that you were looking for, now we can imagine asking questions in Control+F and having it do the semantic similarity matching to match us with a highlighted text sequence in these documents, and it can do it with really large documents, like collections of documents, not even just a single document. And there are some interesting case studies of these systems. Then we see the generator, the retrieval augmented generator. This is a really exciting new model that it's a language model that prepends the context of these retrieved documents, and it's trained in this way, so it's learning with context. So say you want to ask it a question where this is known as multi-hop question answering, where the model has to combine information from multiple sources. The retrieval augmented generator is a really great framework for learning how to integrate information from multiple contexts in this parametric language model that has this context prepended to the input of the question. So it would be context A, all this, context B, all this, question, mask, then generates the answer. So next up, we have this really ambitious task of summarization, where we have pre-training techniques like the Pegasus model from Google. That's a better pre-training task, more aligned with how to use this self-supervised learning for the downstream task of summarization. And this has been implemented in Haystack to do this summarization of these articles. And then the pipeline is describing some of the techniques that you can use to connect these different components together of these semantic search systems. So I really enjoyed reading this. It's a really interesting article describing these recent advances in Haystack. So with the excitement of Haystack and building these new search engines with these cutting-edge advances in natural language processing, one of the most kind of cutting-edge and ambitious ideas is long-form question answering. This could involve summarization, question answering, or maybe chatbots, any system that has to produce, say, a paragraph-length answer. So one of the common benchmarks for one of the data sets for testing this out is Explain Like I'm 5, and Hugging Face Datasets is a really awesome library, has implemented this. So if you want to play around with this, it's as easy as like from dataset, import load dataset, ELI5 split equals train, something like that. And now you can instantly get a sense of what this dataset is. So it's this idea of summarizing these documents, answering questions. Why does water heated at room temperature feel colder than the air around it? And then the summary of the different contexts. So this is an example of these kind of long form question answering data sets. And these authors have built this system that's topped the leaderboard, and now they're coming back and saying, here are some of the major problems that we've found in our investigation with these models and these data sets. So the first thing they find is that there is a significant overlap in the train validation questions. So can you protect electronics from EMPs, solar flares? If so, how? They find that there's already a question about how does an EMP ruin electronics? In the training set, there are a few questions that they find in the training set that help with the validations that are heavily overlapped with the validation, and maybe they're memorizing these high frequency patterns as a result of this overlap. Do I have any thoughts on this? I mean, I'm not sure. It seems like you probably need some kind of similar question to answer this. Like, it seems really hard to exactly pinpoint how you're going to have the distribution shift between the trained tests with respect to answering these kinds of knowledge-specific questions. And there's another interesting data set titled knowledge-intensive language tasks that kind of reminds me of this kind of area of trying to design these tasks that require knowledge. The next finding is that simply retrieving random answers actually has a pretty high Rouge score. So using this metric of the Rouge L score, it actually has a pretty high overlap with these random answers compared to the gold answer. So that's obviously not good. Then conditioning the answer generation on random documents instead of relevant ones doesn't improve its factual correctness. So I'm not sure if this is a product of the models they use. I think they discuss that they use the Realm style retriever, which is similar to the retrieval augmented generation thing. It's just a different strategy of rebuilding the index during training. So a more specific detail. Yannick Kilcher has made a video that dives into this paper if you're curious about Realm. So they're showing that conditioning on this context isn't really improving performance. So we have 19, I think lower is better based on interpreting this. They say that 19 compared to 25 using random context as the background. And then finally, annotators find it difficult to judge long answers with repetition and correctness of technical content. So, it is difficult to construct these data sets. So this is an interesting paper. I'm definitely excited to read more into this, hurdles to progress in long-form question answering. Another really exciting piece of news in deep learning and AI this week is the release of a new data set of expert annotated legal contract reviews. So they discuss how this has over 13,000 annotations, and let's get into some of the details of the cost of constructing this data set. So they note that before annotating contracts for our data set, each law student annotator went through contract review training that lasted 70 to 100 hours. They also had to adhere to over 100 pages of rules and annotation standards that were created for annotating this data set. So they note that a conservative estimate of the value of this data set is over $2 million, and this is calculated from each of the 9,283 pages of legal contracts were reviewed at least 4 times, each page requiring 5 to 10 minutes, and assuming a rate of $500 per hour. So I'm not sure if that's $500 per annotator, or if that's for the whole group of annotator per hour working on these pages. So this is the overall idea of the data set illustrated in figure 1. We have these different contracts, and then we're labeling them into the clauses. So the clauses have these different labels, and that's the downstream task that they're going to be discussing. Is you take a subset of the contract and you classify it into some labels. So maybe let's just look at that to get a better sense of this. So you'd have these categories: renewal term, governing law, licensing, and then you have the description of that. So these are some of the different label categories for clauses in the contract documents. And then you see some of the performance of training these models, and probably the most interesting curve that you'll see in this paper is figure 6, which is showing the benefit of having more labeled data. So this is a really interesting data set for legal natural language processing and bringing natural language processing to some really interesting problems. One of the hottest topics in deep learning right now is the emergence of a new programming framework, JAX. So in this evolution from TensorFlow and then PyTorch gained all this traction, now we have a new library known as JAX that is gaining a lot of momentum, and we have an update to the JAX documentation this week. Tutorial on going through these 6 different categories. JAX is accelerated NumPy, just-in-time compilation, automatic vectorization, advanced automatic differentiation, pseudo-random numbers, parallel evaluation, and stateful computation. So each of these different tutorials comes with a Google Colab notebook that walks you through these examples and shows you how it's different, what kind of things you can do with JAX. And personally, going through this, my favorite thing is these higher order derivatives. So there's a branch of research that takes these gradient through a gradient, the teacher-student learning, or there's also second order like optimizers like shampoo. But I'm really interested in these ideas like mammal, and I think even the generative teaching networks paper has this gradient through a gradient idea. And I think that one thing that motivates me to want to learn more about this JAX framework is it looks like doing this Hessian calculation where you have this second derivative thing. It looks like this would be easier to implement with JAX, and that there's probably more support for it, and it's more low level for doing it. They also talk about doing things like stop gradients, having these straight through estimators, things like that. So overall, it seems like a really interesting framework. Personally, I'm not yet convinced on diving in and learning this all the way. I'm still kind of strengthening my knowledge of PyTorch and TensorFlow, and I don't think this is quite ready for me, but I imagine that if you're doing things like, I saw some people talking about optimal transport implemented in JAX, and these kind of cutting edge ideas I think are better for JAX. Hugging Face continues to roll out some really exciting features for making natural language processing more accessible. Now we have the AutoNLP tool that I think is still in beta, but is really close to being finished. And AutoNLP, this video from Abhishek, a really awesome walkthrough of this, is going to be a command line interface. So skipping ahead to showing the command line interface. It's going to be a command line interface where you create a project, you specify a language, and then you give it some metrics, and it's going to do this automatic hyperparameter tuning for you just with this single command line interface. So this is a really interesting project that should make more people interested in using natural language processing. Facebook AI has open sourced a library for reproducible, self-supervised contrastive learning. You can see in the list of configurations some of the different implementations that are available with this VISSL library. We have Moco, Jigsaw, this is like auxiliary task self-supervised learning, SimCLR, Suave, and then we also have implementations of supervised learning. So the key idea here is you define this configuration file where you set the configurations of, say, the SimCLR learning, and you have these YAML files where you define all these different things like the data augmentations you want to use, the head for doing the projection of the feature representation, the optimizer, and all these kinds of ideas. And you also have a support for integrating a custom data set. I'm not sure exactly what that is. And then you also have these different util functions for doing proper benchmarking and feature extraction and these kinds of ideas. So overall, I think it's a little clunky to use from my first take and trying to get a sense of this, but I do think that this is definitely an interesting direction for trying to standardize these self-supervised learning experiments. And it's really interesting if all you have to do is point it in the file path to your data set, and then just a configuration file that makes it really obvious how to just customize the SimCLR representation learning for whatever task you're interested in doing. Thank you so much for watching this edition of the AI Weekly Update from Henry AI Labs. Please leave a comment if there is any piece of content covered that you think that I made a mistake or you have a question about, and I'd be happy to answer it in the comments of the YouTube video. Thanks for watching. Please subscribe to Henry AI Labs for more deep learning and AI videos, and I'll see you next week for the next edition of the AI Weekly Update series.